So let's see here. I'll begin with I have a bad habit of not plugging in my mic cord. Sure, I actually did that. Yeah. Let's see here. So, read you a couple verses here from Colossians chapter 2, verse 6. Therefore, as you have received Christ Jesus the Lord, so walk in him, having been firmly rooted and now built up in him, established in your faith, just as you were instructed, and overflowing with gratitude. See to it that no one takes you captive through philosophy and empty deception, according to the tradition of men, according to the elementary principles of the world, rather according to Christ. For in him all the fullness of deity in bodily form dwells in bodily form. And in him you have been made complete. He is the head over all, and the over all rule and authority. That's Colossians chapter 2, verses 6 through 10, I think. I'll begin with a word of prayer. So, Heavenly Father, we thank you again for this day. I thank you for this class. Just ask you to bless our work, help us to understand a little bit more about differentiation, and I just pray that the students who ask good questions and learn what they need to from this class. Lord, in your name I pray, Lord Jesus. Amen. All right, so let me kind of go around the room here. So I'll start with this one. So what do you guys think? Right? Wrong? Mostly right? Mostly wrong? What's your opinion?
I'm gonna say right.
You're gonna say right? You did it. That I like that. Good. It's confident. You should be confident. That's good. It's good. Let's see here. So we got. Let's see here. So you're first of all you're just rewriting the expression, and then I mean, this is not bad, but what we want to do is something like, sort of work on. We want to show where we're differentiating, where we're just doing algebra steps, that kind of thing. So not wrong, really just formatting issue here, So this one, like you said, this is 2x, and then you got a minus sign of the square root of x plus 3, excellent, and then times the derivative of x plus 3, which is 1 over 2 times the square root of x plus 3, right? And yeah, and you could rewrite it like that if you wanted to. Sure. Yeah, well, it's mostly just, so like it's floating, like this is expression and then this expression. So like, are these equal? Like what's going on here? And like, I know what you're doing because I just asked you to do it, right? But when we're writing solutions, we want to use the differential notation and so forth. But very good. Let's see here. What do you think? Is the next one going to be right? I hope so. Uh-oh. Let's see what we got here. Not sure this is going to show up in the camera or not, so we tried. Let's see here. So you're like x d dx of e to the minus 3x plus e to the minus 3x times d dx of x. Very, very good. So product rule. Very good. And then we have the derivative of e to the minus 3x is minus 3 e to the minus 3x. Very good. 1. And so that's pretty good. Now I'm very, I like to connect my equalities if that's what it is. Alternatively, if you don't want to do that weird thing I just did, it would be good down here to write like, you could do something like this. You could be like, okay, this is y. So what we're looking at down here is dy dx. Come on. So we just like to have some explicit notation that says this is the derivative. But very good. I'm just quibbling over notation again. Same quibble. But, you know, better, not floating, but okay. All right, so you've got the f. Okay, so we're taking the derivative of the numerator function here. This parenthesis right here needs to close right there. See that? So then we've got minus cosine t times the derivative of the denominator, very good, divided by denominator squared. So we're using the quotient rule here. Excellent. All right, so we've got minus sine t plus 3, and well, see, I don't know. So we're doing ddt here, right? And so I'm not being too critical. I know you guys aren't used to writing with whiteboard markers, right? So I'm worried that that's a ddx, but maybe it's not. See that? Maybe it's not. Because we should be doing ddt in this problem. So, all right. Let's see here. So minus sine t plus 3, derivative of t plus 3 is just 1. Very good. So you got that down there. And then over here, so here's a mistake, but I think you realize that. So this right here is a product, right? So we have to do product rule there, right? So let me just put the answer up above it, because that way we can all see it. So let's see here. We're going to have minus t e to the minus t sine of t plus 3 from that first derivative that you did. Oh yeah, that thing. All right, so then minus the cosine of t plus 3. And then I'm going to put what's in the circle in like a big parenthesis here. So what that would work out to is e to the minus t e to the minus t from the product rule. And then all divided by that t e to the minus t squared. And I'm not going to fuss about simplifying this one. But you could definitely simplify this a bit, because there's a common exponential on every single term, both in the denominator and the numerator. So you could factor and simplify an e to the minus t out of this guy. So hey, by and large, very good effort there. Just need to watch out for the product rule. And I did stop you short of time, so you probably were on your way to doing that anyway. Let's see here. So next up, so the numbering of these examples is a little bit wonky, but anyway, now we're to example 3. After we're done with examples 2 and 9. All right, so here, very good. We need quotient rule. I agree. And so the derivative of the top, 1/2 x to the minus 1/2, very good, times the denominator function, like so. We got correct. Then minus the top times the derivative of the bottom. The question is this the derivative of the bottom? I think no. So, that's kind of funny. So like the mistake in this problem and the mistake in the last problem exactly in the same spot, you know? The derivative of the denominator function, because I made it weird. But so this is fine, I believe. Oh, no, it's not. That is supposed to be 2 to the x. 2 to the x and x squared are very different functions.
I think the one above it is 2x to 2 to the x.
Oh. Okay, yeah, we need to be careful about that. We need to, we got to write things in such a way that we don't do that. Okay, so I'm going to just erase this part because that part's not quite right. But we can fix it. I'll fix it up here. So what we're working on, and again, just to be clear, the derivative of this is equal to that. All right, fine. So the derivative of x squared times 2 to the x minus cosh x is equal to, sorry, I keep finding myself snaking around here like this. But so we got a product rule. We've got a product rule in play there, right? And the product rule that we face is this. So the derivative of x squared is 2x. Then I've got times 2 to the x, right? Plus x squared times the derivative of 2 to the x. Now the derivative of 2 to the power x, we worked out last class. It is the natural log of 2, times 2 to the x. That's how we differentiate 2 to the x. Very different than x squared. So that's just the derivative of this first two terms. And then we've got minus sinh x, because the derivative of cosh is sinh. And so that all goes here. I guess I could factor the 2 to the x out. I don't know. I'm just going to write it again. So 2x times 2 to the x plus x squared, natural log of 2. You could clean this up a bit, but I'm just going to leave it, all right? Because I'm not trying to talk too much about simplification at the moment. I'm just trying to talk about differentiation. Some of your homework problems, I just say differentiate, don't simplify. That would be what I'm doing right now. Other problems, I say differentiate, simplify if possible. So by that I mean differentiate and simplify if possible. So, sorry. I'll try to stop my trollish comments. Yeah. It's the end of the coffee pot. It's not good. I'm still going to drink it. All right, so here we've got a proposed derivative of tangent cubed secant theta plus theta cubed. And what I'm looking at here no. So not. I mean, you may be in the middle. I think I stopped you mid thought. So I'm just going to erase. Sorry, I can't fix it. Which isn't to say it wasn't fixable. It's just to say I'm not thinking of it the way you were thinking of it, whatever that was. So let's just go on here. So what we want to do is we've got the derivative with respect to theta of tangent of theta cubed. That's what that means, tangent cubed theta, right? So that derivative times secant theta plus tangent cubed theta times d d theta of secant theta. Why am I doing that? What's that I just did? That's called the product rule because we have a product of tangent theta and secant theta, right? So that was these two terms. Not done with it yet, but that's this, starting point. Then what? Derivative of theta cubed. Well, that's easy. I'm pretty sure you had that right. I just erased it. So plus what? 3 theta squared. So that just sits over there. It doesn't mess with anything else here. What's the derivative of tangent cubed? Yeah, 3 tangent squared. But then we have to do what? We have to multiply that by the derivative of tangent, which is secant squared theta. Right? And then we've still got the original secant theta sitting out there. And then over here, I've got plus tangent cubed theta. Derivative of secant was secant tangent. We worked that out, I think, yesterday. You mean you expect me to remember that? Yeah, I do. Like, you need to memorize it if you don't know it already. So just to emphasize what went on here, this term is these two, and this guy is this right here. All right. I think I'm gonna take a second to simplify this one because I think it's worth the effort, and it wouldn't burn a lot of class time or be hard to follow. So we can simplify this, right? Like what's common here to both? I've got a tangent to the fourth. Maybe a good step here. One more step. So that's 3 tangent squared theta secant cubed theta plus apparently tangent to the fourth theta times secant theta plus 3 theta squared. Yeah. What's that? So what we can factor something out here. What can we factor out? It looks like we've got I think we can factor out tangent squared secant. Like that's the most I can pull out, right? And if I do that, I'm left with a 3 secant squared theta plus what? Tangent squared, I think. Plus 3 theta squared. Yep.
I have a quick question.
Sure.
So, in the second
Uh-oh. What have I done?
could you explain how the derivative of tangent theta cubed also includes the secant?
Oh, sure. So I'm going to stop with my simplifying ways. I guess I would say we could have, if the question just said find the differentiate, don't bother to simplify, that would have been the answer. If I'm simplifying, I probably can go further here because I can, I can take the tangent squared. Tangent squared is secant squared theta minus 1. So I could actually collapse this into like 4 secant squared minus 1. I could further reduce that if I wanted to, but I'm going to answer your question instead. So your question was, why is my tangent cube derivative as it is? That's a good thing to investigate. So let's talk about it. So what we're doing is we're differentiating u cubed. But here u is equal to tangent theta, right? So that gives me 3u squared du d theta by the chain rule. But that is 3 tangent squared theta times d d theta of what? Of tangent theta. What's the derivative of tangent theta? It's secant squared. So that's 3 tangent squared theta times secant squared theta. So that's why I have what I have up there. That's these terms here, right? Does that make sense? Yeah. Again, this one, it's tempting to keep simplifying this, but I'm going to focus on the differentiation for now, okay? There are applied problems where the simplification matters. Like especially later, soon in this course, we'll ask questions like, where's the maximum of something? Where's the minimum of something, all right? So to solve those kinds of problems, you look for where the derivative is 0. But to solve for where the derivative is 0, you have to like simplify the derivative basically. Otherwise you can't hack through the equation, the derivative equal to 0. Derivative equal to 0, that equation is only as easy to solve as the formula for your derivative is to understand. Let's see here. Continuing. Man, I should have got you guys better markers. I'm not sure this is actually going to show up on the silly camera. All right. So yes, true enough, inverse tangent is the inverse tangent of tangent restricted to minus pi over 2 to pi over 2 non-inclusive. Very good. That is true. So y equals inverse tangent x means x is tangent y. Very good. Now you differentiated implicitly that equation. You get 1 is secant squared y times dy dx. Very good. Solve for dy dx. We get 1 over secant squared y. Very good. I'm going to have to stop you right there. No need. You probably came around. Now, I think I'm going to have to erase the... Is it okay? I'm going to erase this. There's an easier way. So it was all, because that unfortunately is not true. There we go. Up to this point, perfect, just perfect, all right? Now, so here, listen, the thing to remember is, let's work it out again. Cosine squared y plus sine squared y is equal to 1. If we divide by cosine squared, we get 1 plus sine squared y over cosine squared y is equal to 1 over cosine squared y, but what's that? This is exactly the identity 1 plus tangent squared y is equal to secant squared y, right? So this is like one of our basic pre-calculus trig identities. We need to know it. I say you need to know it, but I'm showing you how to derive it. In fact, all you really need to know is sine squared plus cosine squared and how things hold together through like algebra, you know? So anyway, in view of our substitution right here, this is actually 1 plus x squared equals to secant squared. See that? In this context, tangent of y is x. So really, your denominator, 1 over secant squared y, is simply 1 over 1 plus x squared, you see? That's it. And then, so this one just doesn't, it doesn't face the same, what's the word, subtlety as the one we did yesterday. This is actually an easier one in terms of the analysis at the end of it. I mean, and so there it is. The derivative of inverse tangent is 1 over 1 plus x squared. Now, this makes sense, by the way, because what is tangent? Well, you know, what's the derivative of tangent? Yeah, secant squared. Where's that positive? So I'm getting ahead of the story a little bit in here, but one of the things we're going to do going forward is to use the sign plus or minus of a function to decide whether it's increasing or decreasing. Now that's justified by something called the mean value theorem. We'll have to look at that. But it's kind of intuitively obvious, right? Like if the slope of the function is positive, the function's increasing, right? The graph is going up as you look at the graph going left to right. Yeah? If the slope is negative, that means the function's going down as you read the graph from left to right. So since the derivative of tangent is secant squared, that is manifestly positive or undefined, right? Secant squared is undefined the same place as tangent's undefined, namely at half integer odd multiples of pi, like plus or minus pi over 2 or plus or minus 3 pi over 2, those places. So like we expect that the formula for the derivative is, you know, positive, and it is 1 over 1 plus x squared. It just, the nice thing about this one is there's no kind of algebraic decision to make plus or minus in the solving like we had last time, you know? Anyway, very good, very good. Let's see here, example 5. Sonic seal of approval, totally correct. Yeah. I think, wow, something's funny over there. Did you guys hear that? Yeah, okay. Yeah, I mean, it pains me to kill Sonic this way, but yeah, sorry. No. This is not how that goes. So let's work through this. So the way to, if you've got a product of not 2 things but 3 things, how does it go? Well, see, a product of 3 things we can look at as a product of 2 things, right? So this is d dx of x squared times e to the x times 3 to the x plus x squared times d dx of e to the x 3 to the x, right? Which I'll rewrite another time as d. I'm not going to simplify the derivatives just yet, guys, because I want to point out to you guys the pattern. And like, I'm going to write this as a theorem for us, okay? So that's x squared times d dx of e to the x times 3 to the x plus x squared e to the x d dx of 3 to the x. So this is the triple product rule, which I'm, well, let me finish this one and then I'll talk more about the triple product rule. This is 2x e to the x times 3 to the x plus x squared e to the x 3 to the x. I like the way that sounds. Plus x squared e to the x natural log of 3 times 3 to the x. This one, I got to simplify this one. So you got yourself an x e to the x 3 to the x times 2 plus x plus natural log of 3 times x. So this one's worth talking a little bit more about. Like let's kind of sit and do some things with this example before we go on with it. First of all, I want to point out to you that, as I was saying, there's a triple product rule. The triple product rule looks like this. If you've got ddx of abc, the way it works is dA dx bc plus a dbdx times c plus ab times dc dx, like that. So you need, so as many terms as you're multiplying, you need the sum of that many summands, and each summand has the derivative of just one thing in the product differentiated. That's how the product rule works. What do you guys think the product rule is for 4 things? What if I had like A, B, C, D, and I'll use the prime notation this time. It would be what? A prime, B, C, D, plus A, B prime, C, D, plus A, B, C prime, plus, D, plus A, B, C, D prime. Can you do the product rule for 5 things? You see the pattern? It's not. Okay. It's more interesting if we start thinking about higher derivatives. We should talk more about higher derivatives here once we're done with these exercises. Now, so question for you guys. If we look at f of x equals to the function we just differentiated here, namely x squared e to the x times 3 to the x, right? Then y equals f of x has horizontal tangent where? So that's my question. Can you guys figure that out? What do you think? At 0, that is one answer. Very good. Because 0 would make df dx equal to 0. So really I'm just asking the question, can you guys solve the equation df dx equal to 0, right? So in other words, we're looking at, put this equal to 0. So what are the solutions? So you guys are like, x equals to 0 is one place where we have a horizontal tangent, and where else? See, because if x is equal to 0, it makes this product equal to 0, right? How about e to the x and 3 to the x? Is there any hope of those ever being 0? Those are exponentials. The exponential graph has a horizontal asymptote of like the x-axis. It never goes through 0. E to the x and 3 to the x, those are always positive. Whether it's x goes to infinity or minus infinity, either way, it never gets to 0. So these guys don't help you. They don't give you any zeros. How about this? Could this be 0? So set it equal to 0. What do you get? We have 2 plus x plus the natural log of 3 times x equals to 0. That gives us x times 1 plus the natural log of 3 equals to minus 2. So x equals to minus 2 divided by 1 plus the natural log of 3. That is the other place where you have a horizontal tangent to the graph here. So these 2 points, x equals to 0 and x equals to minus 2 over 1 plus natural log of 3, these are called critical points of the function. They're places where the derivative is 0. If we were to study where the function's minimized and maximized, we'd find out it had to happen at these points, possibly, if anywhere. Which is not to say that it's minimized or maximized there. There's something else that could happen. Okay, so there's that one. Let's see here. we got sine squared of u. So we've got 2 sine of, man. It's a good try, good try. So I'm going to leave this here because I want to try to contrast that with like the answer here. So let me just kind of focus on, first of all, like understanding, let's try to understand the pattern here. So the question is really, what's the outside function? So I think, all right, yeah, I guess that's the kind of question. So really we're looking at sine of pi theta squared, right? So the u is not pi theta. The u is what? This makes my inside function actually sine of pi theta, not just pi theta, right? Because it's the sine of pi theta that we're squaring. So this is actually a double composite. It's like a composite of a composite. It's like an onion, you know? But just kind of a boring onion. It's only got three layers, I guess. So I get 2u times dd theta of u, but u is what? Sine pi theta. Right? Which gives me 2u times the cosine of pi theta times dd theta of pi theta. See, I need 2 applications of the chain rule here to get through it. Because I've got the inside function, which is sine, but I've also got the inside function, you know, which is pi. And then, you know, answer, we've got ourselves a 2 sine of pi theta times the cosine of pi theta times pi. I'll just bring the pi out front because I like to put my pi's out front. There you go. That's it. So you're close, but you got to understand that the inside function's sine. So you have to differentiate the inside function, which gives me a cosine. So you skipped from the middle function to the, I don't know how to say it. Oh, yeah. Okay, so I think what we're looking at here is a proof that the derivative of cosh x is equal to sinh x. I'm going to just not say just right here, and like we just not look at the not true. We can't just flip sinh to 1 over sinh. This is the kind of creative algebra I often see on tests. It does not warm my heart because I want you guys to do better. You know, you guys got to chase down your algebra demons and kill them. I mean, exorcise them, right? Yeah. Algebra exorcism, something like that. You guys are probably not Catholic, but you know, we need to chase down the algebra. So I know you're being facetious here, I think, but you cannot just flip sinh to 1 over sinh like that, and you can't just like ignore the -1 either, right? So I'm going to have to erase this. Because what does the -1 mean there? It's not, so this is not, first of all, this is not the question. There's a related question, well, it's not exactly related, but it's a different question, which is 1 over cosh. That is a different thing. That is the derivative with respect to x of what's called the hyperbolic secant of x. That's a different question altogether, all right? This is the inverse hyperbolic cosine. So we're going to have to go back and we're going to have to use the technique that was mostly successfully used in example 4 over there. So we start by writing y equals inverse cosh of x. Then we take the cosh of both sides. We get cosh of y is equal to x. Then we differentiate implicitly, right? Steps 1, 2, 3, and so forth. Differentiating implicitly here gives me sinh of y times dy dx is equal to 1. All right? And then I solve for dy dx. I've got 1 over sinh of y. Now at this point, I want a formula in terms of x, right? So I need to pay mind to what are the identities which govern hyperbolic cosine. The major one is this: cos squared y minus sinh squared y is equal to 1. So in view of that, that says that, what does that say? That says that sinh of y squared is equal to cos squared y minus 1, I think, right? In other words, the sinh of y is got to be plus or minus the square root of what? What was cos? Well, cos was x, right? So we're looking at the square plus or minus the square root of x squared minus 1. Now that begs the question, what are we inverting? Do you guys know what the graph of hyperbolic cosine looks like? Maybe not, right? Let's talk about it. So the graph of hyperbolic cosine, and so we're talking about y is equal to 1/2 e to the x plus e to the minus x, right? That's your hyperbolic cosine. When you plug in 0, you get 1/2 of e to the 0 plus e to the 0. What's e to the 0? Well, e to the 0 is 1. So 1/2 of 1 plus 1 is 1/2 of 2, otherwise known as 1. And if you study this, what you'll find is that, well, we can kind of figure it out, right? Because we know that the derivative of cos is what? Yeah, sinh x. And well, I guess if you knew the graph of sinh, that helps. The graph of sinh looks like this. So if you already knew that, that's helpful, because then you can understand, okay, so the derivative of cos is sinh. That means sometimes it's increasing, but sometimes it's decreasing. You can also think about limiting behavior. If you think about this formula here, e to the x plus e to the minus x, what happens as x goes to infinity? Think about this. As x goes to infinity, e to the x gets huge. E to the minus x, nothing, right? What happens as you go to minus infinity? The opposite way around, right? As you go to minus infinity, e to the x becomes puny. E to the minus x blows up. So whether you're going to plus infinity or you're going to minus infinity, either way, you're going to infinity for this function. So it's essentially, ignoring the local details, it looks more or less like x squared plus 1 to the limits of my artistry here. This is the graph of cos. It's more like a goalpost, though. I mean, understand that these are both exponential growth. So it's much, much steeper than like the polynomial x squared plus 1. Okay, so then that begs the question, it's the inverse hyperbolic cosine of what? See, because it's not a global inverse, because this is not a one-to-one function, right? So here's the convention. The convention is that when you talk about inverse hyperbolic cosine, you're talking about the inverse of cos. Just to get to the point here, inverse hyperbolic cosine is actually the cos restricted from 0 to infinity inverted. It's the inverse of cos with respect to that domain. So the actual inverse cos, it's inverting this part of the function, this branch, if you will, right? And so is it increasing or decreasing there? It's increasing, so that means that the derivative of inverse cos has to be positive by what we talked about the other day, which means we choose the plus. So there you go. d dx of inverse hyperbolic cosine of x is equal to 1 over the square root of x squared minus 1. And I'm I'm trying to remember how it goes for sinh, inverse hyperbolic. The derivation of inverse hyperbolic sinh is similar to this. How did this work out for how did this work out for regular cosine yesterday? Do you guys remember? It's interesting to contrast these formulas. Like the derivative of inverse cosine is what? It was minus 1 over the square root of what? It's a very similar looking formula, but it's very different actually. Yeah. 1 minus x squared. Yeah. See the difference? For inverse hyperbolic cosine, like so the domain of the inverse function, right, should be the range of the function. What's the range of the red part? It's just what? It's 1 to infinity. See this point right here is 1, 0. Excuse me, 0, 1. I'm an idiot. And so naturally, this formula only makes sense if x is what? Larger than 1, right? Otherwise, you'd have the square root of a negative number. And look at what else happens. When we look at 0, this blows up, right? Because the inverse function has a vertical tangent at the edge of its domain, just like the restriction of cosh to this has a horizontal tangent right there. So that horizontal tangent for the function, when it's inverted, becomes the vertical tangent, which you're picking up in the divergence of that formula there. Likewise, for cosine, inverse cosine has a domain which is the range of cosine. The range of cosine goes from minus 1 to 1. This is a domain minus 1 to 1, both minus 1 and 1 not included, because those correspond to the vertical tangents for inverse cosine, which are picked up by the horizontal tangents, which are at the endpoints of the 0 to pi domain we talked about yesterday. Anyway. Oh, so yay. All right, let's go on. So you guys have any questions about homework now that we've finished this lengthy in-class example here? Who's calling me? Uh-oh. Crazy Paul. It's not a short call. Good thing I have my phone silenced. When did I silence my phone? That's not a good thing. How long has my phone been silenced? I don't know. Maybe I'm part of your generation. I feel like I don't know how to use a phone. Actually, do you guys know how to use a phone? You know. But do you like pick it up and like talk to people, or do you have to do the texting? Or is the communication like picking up and talking, or is it mostly?
It depends on the person.
Or is it mostly like through Instagram or something, or? Nobody just calls anymore. That's what the phone is for. It's for calling people. Yes, okay. Anyway. All right. So, a few things we should talk about, unless you guys have a question. Yeah.
Problem 149. So it's calculated for B.
149b.
Yeah, B.
If I can find it. I will find it. So I have a particular set of skills. Finding your homework problems, one of them. 149, which one?
B.
B or D?
B. B as in boy.
B as in boy? Ah. This is a very easy question. So let's see here. What am I, example 10? Check this out. So if I'm doing the derivative with respect to x of like, oh, I don't know, x times the cube root of x times 1 over x to the 1/5 power. How would I do that? Now, it may not seem like I'm answering your question, but give me a second. We got to lead up to it. So how do you differentiate this? If you're thinking use the triple product rule, you're thinking wrong. We should do what? We must return to our review of algebra, right? First thing to do is simplify before you differentiate. When you can, you simplify. So this is what? X to the 1 plus what? 1/3 minus 1/5, right? That's what I'm up against. So let's see here. I've got, I guess we got to go 15ths, right? 15 plus 5 is 20 minus 3. I think we got 17/15ths. Do you guys agree or disagree? I mean, you could pick up your calculator and check me on it. I think my calculator's in my office at the moment, so I guess I could do the Google. Confirm or deny? Oh, I've got thumbs up. Okay. Okay, so that makes we both agree on it. That means there's a consensus. All right, so it's true. And then we power rule this thing, right? So this is 17 over 15 times x to the 17 over 15 minus 1, also known as 2/15. Hooray, done. All right, ready? Example 10, part 2, dd, let's say a, of x inverse hyperbolic tangent of x cubed plus 7 times the cosine of the sine of x plus 3 times the cube root of the tangent of x plus the cosine of x minus 42. Is that enough? I think that's enough. What's this equal to? Now, there are two possible answers here. All right? The one possible answer is that it's a horrible, monstrous expression because x is a function of a. All right, if x is an arbitrary function of a, I don't want to try to write the answer down for this. It would be horrible. We don't even know how to differentiate inverse hyperbolic tangent yet, do we? We can learn it, though. We can figure that out. I think I'm going to save that for tomorrow because I'm trying to I have done this, how to find the derivative of the inverse function yesterday. We did it today. I'm going to do it again tomorrow. It is something you need to learn, but I think it helps if you see it multiple days layered. But the answer here is if x is constant in A. If x is constant in A, what's that mean? That means that dx dA is equal to what? What does it mean to say one variable is constant in another? It means that if you vary the variable, the other variable does not change. So the change in x as a changes is 0. And so if you think about what that means logically, if you apply the product rule and the chain rule and all that jazz to this expression, every single last one of those gets multiplied by a dx dA at the end of it, right? Which is 0. Or just to put things in more common terms, if x is constant with respect to a, then so is all this. And if it's constant with respect to a, the derivative is just 0. So the answer to your question is, yeah. Hey, here's another one. This one I always get you guys on test. I'm going to show you one of my secrets. Check this out. If I put this on test 2, what are you guys going to do? There's two paths you can go down. One of them you want to be on. The other one, I take your points. What's that? What we got? There's two choices here. 0. The other choice is 3 pi squared. Which one would you like? 0 is the correct choice. That's right. Because we're not differentiating with respect to pi. At no point in any of my courses will you see me use pi as a variable. For me, pi is the number 3.14 blah, 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 blah. It's the ratio of the circumference to the diameter of a circle, right? It's an interesting number. I mean, people have spent their career calculating digits of pi, if you can believe such a thing. Okay, hey, let's talk about higher derivatives. Oh, if you got another homework question, you can ask. I just need to talk about higher derivatives here before we end business today. Well, let me give my quick spiel about higher derivatives, and then if you have more homework questions, we'll come back to them, okay? So, definition, the nth derivative of f of x is equal to d dx of the n minus 1th derivative of x for n greater than or equal to, well, 1. And if we have, of course, you know, the 0th derivative of x, by definition, is just f of x, okay? So, like, for example, f prime prime of x, we also denote as f2 of x. What that means is d dx of f1 of x, right? So d dx of f prime of x, which, to complete this litany of somewhat redundant notation, that's d squared f dx squared. So we've got all these different competing notations for higher derivatives. So you can do prime prime for a second derivative. You can do d squared f dx squared for a second derivative. What do you guys think the notation for the third derivative is going to be? Cubed? Yeah, we could do d cubed f dx cubed, like that. Or we could do f prime 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 prime. It's just a matter of like civilized notation. You really, as a matter of custom, shouldn't go past 3 primes. Or like it's just a custom that people will write f prime prime. Like the third prime of x, you'll see that in like publications and stuff like that. But as a general rule, anything past 3, you're going to do something like 4 of x, just because, you know, it gets a little bit tiresome to try to count the number of primes at some point. All right? So these are higher derivatives. Definition, if we have x is equal to the position at time t, then v equals to dx dt is velocity at time t. And if we look at dv dt, this is by definition the acceleration, which is, by the way, the second derivative of the position. So the higher derivatives are important for physics because acceleration is like, you know, a big part of Newton's laws, right? F equals ma, that's acceleration. So we need second derivatives to describe physics for sure. Let's see, what example am I on? 12. Let's work out a couple higher derivative problems. How about this? If I have f of x equals to x to the 4th plus 3x cubed plus 2x squared plus x plus 1. What's the first derivative? I got a 4x cubed plus 9x squared plus what? Plus 4x plus 1, right? What's the second derivative? Yeah, 12x squared plus 18x plus 4. So every time we differentiate, we drop the degree of the polynomial by 1. You see that? What's our third derivative? Oh, by the way, in physics, the third derivative is called the jerk. Because it kind of describes, the third derivative of non-zero describes the motion being sort of like jerky. For example, if you've ever been on a railroad, which has like a straight track and then it goes to a curved track, if you study the motion of that, you'll find out that one of the variables has a non-trivial third derivative corresponding to when you go from like the straight track to the curved track. It goes like, you guys know what I'm talking about? Like no one drive, like we don't call on the phone. We're certainly not riding a train, right? What do you think this is? 1860? All right, anyway, f prime prime prime. And then fourth derivative, what do we got? 24. How about the fifth derivative? We got 0. How about the nth derivative? It's 0 for n what? Greater than or equal to what? 5. This is a general theorem. If you think about an nth order polynomial, right? If you differentiate n plus 1 times 0, okay? There's another example where I can calculate the nth derivative very easily. How about this one? Calculate me the nth derivative with respect to x of e to the x. What happens if you differentiate e to the x n-fold times? The first derivative gives you what? E to the x. How about the second derivative? E to the x. We could be here all day, right? It's just e to the x all the way down. Now, of course, if you did something like d dx of e to the minus x, well, that'd be a little bit more interesting, right? Because then you got to think about it. Yeah, so yeah, let me work this out here. So like d dx of, we'll see the pattern pretty quickly. So we've got minus e to the minus x for the first derivative. How about the second derivative? We get minus e to the minus x, right? So the minuses cancel. We get a plus. So if you tilt your head and squint, you can see the pattern here. The derivative of the nth derivative of e to the minus x would be minus 1 to the n times e to the minus x. Like that, that's the pattern you can start to see if you study it. Do you guys agree? Like if it's even, when we differentiate an even number of times, we get an even number of minus 1s multiplying from the chain rule from each application of differentiation. If it's odd, we get an odd number of minus 1s, which when you multiply them together, you get minus 1. So the formula is just minus 1 to the n times e to the minus x. Anyway, there is an interesting question in your homework. One of the ones I marked with a star, which was, what's the higher derivative rule? Like, we have a product rule, right? What's the product rule for second derivatives? Do you guys know? I mean, you shouldn't know. We've just started talking about second derivatives here, right? But we'll do some physics example tomorrow to try to bring that to life more, okay? I don't want to hurry it at the moment. This one's easy. We can do this in like 3 seconds. So if you take fg prime prime, what happens? So in the prime notation, second differentiation just looks like you differentiate once, put some parentheses, differentiate again. Right? So the first derivative, by the product rule, gives us f prime g plus fg prime. And then we differentiate all that. But then by linearity of the derivative, we've got f prime g prime plus fg prime prime. We got to look at my parentheses to understand what I'm saying. But then we do the product rule for each one of those. What's it give us? It gives us an f prime prime g plus f prime g prime plus f prime g prime plus fg prime prime, which we can simplify to f prime prime g plus twice f prime g prime plus fg prime prime. And that's the double derivative product rule. Do you guys remember the binomial theorem? Like how we multiply out a plus b squared? We get a squared plus 2ab plus b squared. It's like that. If you tried the third derivative product rule, you'd end up with the same pattern, but with like a 1, a 3, a 3, and a 1. If you tried the fourth derivative, the pattern's going to be like a 1, a 4, a 6, a 4, a 1, and so forth. You're going to find binomial coefficients coming up in the higher product rules. So anyway, that's a challenge homework problem there. But I'm just telling you the start of it. I'll shut up. Thanks, guys.